Hello everyone and welcome to a new discussion which is on groundwater exploration. This is part 11. So far we have discussed that in especially the one technique of surface geophysical method which is electrical resistivity, and sometimes we may get very good results as we have discussed, but in certain conditions we may not get good results. So then the next geophysical method which is available to us is seismic method. So in which a seismic might sound an earthquake, but the concept of vibrations is exploited in seismic method. So this is not exactly in that sense. So in this method a vibration or a shock is generated on the ground, maybe by an explosive device which is not very common. Only in oil exploration or in deep exploration for mining and other things the explosive device is used. Otherwise what it is done in the field, a stroke, hammer stroke, and a hammer is hit for the shallow explorations. So generally in case of groundwater and the shallow exploration is performed, and therefore this hitting hammer on the ground, a heavy hammer on the ground can generate vibrations, and then we can detect these vibrations. The differences in the velocity of layers of earth are measured at other point. So at one place you hit the hammer, other place you measure these vibration with the aid of detectors which are called geophones. So basically these geophones are listening the vibrations or recording the vibrations. So it is a quite simple concept in that sense, that at one location a heavy hammer is hit on the ground, and at some distance through geophones we measure this vibrations, and how the velocity, basically how velocity of layers in subsurface condition is behaving. So in geophones are extremely sensitive electromagnetic devices which are capable of responding to very minute vibrations of ground, and here minute vibrations might be a vibration of a moving vehicle also. So while doing such surveys, the noise will be created by movements of vehicles, and that should be removed from the signals, or that should be avoided, and then transforming our response into the electrical signals. So these geophones will convert this response into electrical signals which can be recorded, the frequency and amplitude which are governed by the vibrations. So these electrical signals and their frequency and amplitudes will be controlled by the vibration. So higher the vibration, you may get accordingly higher frequency and amplitude, depends on again the layers or rocks in subsurface condition which are present, and the signals are very small. It is not a very strong signals, because a hammer when it is hit on the ground, how much vibration it will create, and therefore these signals are very small, and therefore they are amplified several thousand times, and before they are recorded. So this kind of technique is employed, and which in brief we say seismic methods, surface seismic methods, which is used. So here what we are seeing, that we can detect even like a slope values are there, and a distance, how with distance and the time things will vary. So this is the reflected signal and the refracted signal. These two types of signals will be getting. Here also we get like these are the nothing but the geophones which are put at many places, and based on this incident or the shot or where the hammer is hit, the incident point and then reflected point are there and refracted. So some will be reflected signals and some would be the refracted signals coming after some time. So that kind of measurements are done. So seismic pulses which are generated by this disturbance at a short point means the hit point, are transmitted radially in all directions and received at the geophones. So how geophones are arranged? So generally again here, since these are also a profiling or give you information along a section of the part of the subsurface, so they are also put in a line generally, because otherwise things will become difficult to imagine. Rays or these signals travelling horizontally called direct rays, which will be recorded. Of course, the first like here direct rays which will be recorded, and reflected and refracted at the boundary. So, first the direct rays are recorded, then what we record the first followed by the rays which are reflected, and finally at the last we will be getting refracted signals which are at the boundary of two different formations will come at later stage. So, the first direct signals are received by geophones, second is reflected signals, and then finally we get refracted signals. So, the seismic pulses which are generated by these disturbance at the point transmitted radially as we have seen. So, the seismic wave fronts and ray paths and travel time plots in respect of an idealized horizontal two layer methods. So, here we are thinking in these terms that there are only two layers, and in that way it is plotted. So, the velocity V1 would always be less than V2. Now, when we think in terms of refraction of rays, then Snell's law, very popular law, is followed, and the sin theta I upon sin theta r equal to V1 upon V2. So, where I is the angle of incidence which we can see here, angle of incidence is here, the theta I, and the angle of refraction can be seen. Then V1 is the velocity in the first medium. So, in the first medium the velocity is there, and then second the velocity V2 is the velocity in the second medium. Likewise we get. So, this is our typical seismic methods exploiting the Snell's law. Now, as I increases, the incident angle increases, the refraction also increases till it reaches a maximum of 90 degree, when sin r, as you know, equal to 1, and at the critical angle of incident IC. So, this critical angle IC can also be expressed in terms of two velocities, that is sin IC upon V1 upon V2, as we have seen. Now, when we see the typical like in case of electrical resistivity, we saw a similar kind of table, and that how different medium or rock behaves differently in terms of electrical resistivity. In the same way, these rocks or medium will also behave differently in terms of this seismic velocity, meter per second, which is measured as meter per second. So, in air this might be 310 to 360 meter per second. In water this velocity is quite high, whereas in loose surface soil dry the velocity is 100 to 300 in range. In case of dry sand it is like an air kind of thing, because dry sands will have no water, and if it is saturated with water, then you know that water will increase the velocity. So, dry sand will have low velocity, dry gravel will also have a little higher velocity, wet clay, silt, sand and gravels will have relatively quite good high velocity. Sandstones again will have more velocity because they are more compact as compared to dry gravel, sand. Shale is another one which will have more velocity. Crystalline rocks will have further more velocity. Weathered and fracture granite will have in the range of 500 to 300 meter per second. Basalt or massive rocks may have velocity in the range of 4000 to 6500. So, that what we are seeing here through this table, the different rocks or medium will have different velocity, and if this is the characteristics of rocks or medium, then we can discriminate in subsurface conditions that which type of rock or medium is existing through seismic method. This is what is attempted here about in seismic method to understand how the velocity will behave in different rock formations, and how it varies with wide limits, because sometimes the limits are very high, like 500 to 3000 meter per second. So, this is again may give some information about the subsurface arrangements or water conditions or water table and so on. So, these wide limits are there depending on the bulk density and water content. So, the same rock if it does not have the water or not saturated with water will give different velocity or less velocity, but the same rock in the lower part of in subsurface condition, if it is saturated with water, will give you high velocity. So, the variations can therefore be interpreted, variations in terms of velocity can be interpreted in terms of compactness of subsurface rocks, porosity, and saturation of rocks, because we have seen that saturated rocks will have high velocity and used to locate interfaces of subsurface layer with velocity contrast. So, if we suddenly get velocity contrast in our recordings, then we can probably say that there are the two different layers in subsurface conditions are existing. Now, this method is particularly suitable for mapping low velocity horizons overlying of adjoining high velocity layers. So, if this contrast really exists in the subsurface condition, then this method is really good, that it will have a mapping of low velocity horizons overlying with the adjoining high velocity horizon. And a typical application of this seismic method is in groundwater, which includes the determination of bedrock alluvium, weathered or fresh rock contacts or contrast we get, and detection of fracture zones and dikes. And dikes sometimes plays very important role towards in the flow of groundwater from one place to another. And if we can detect through these methods, that is always very good. Now, we move to the third type of geophysical method, which we are putting as other methods, which are less common methods, which are applied in groundwater investigations under these geophysical methods, which are very specific to specific geologic conditions, like electromagnetic methods, magnetic methods, gravity methods, and radioactive methods. So, two methods we have already covered, that is electrical resistivity method and seismic methods. Now, we are going which are less commonly used in case of groundwater investigations are electromagnetic method, magnetic, gravity, and radioactive methods. Now, gravity methods based on satellite techniques have been employed in recent times, and I will give you an example which is through the GRACE satellite, and about to understand the groundwater conditions or depletion of groundwater conditions in any part of the earth, because satellites can cover the almost entire globe. So, for India we will be discussing in our future discussion. So, these methods electromagnetic, magnetic, gravity and radiometric methods are adopted usually to supplement electrical resistivity methods. So, whatever the conclusions which we are drawing based on electrical resistivity methods or seismic methods, we can further support our conclusions or can remove all doubts by implying any of these four methods. So, depending on our requirements, how much accurate we are. So, one by one we will be very briefly going through all these four methods which are discussing under other methods. So, first one is the electromagnetic method, and this setup of an electromagnetic method of exploration which consists of transmitter of electromagnetic waves and a receiver. So, whenever some information is sent to the earth either by in form of current or in form of vibration, it has to be received at some distance. So here electromagnetic wave is transmitted and then it is received. So, when electromagnetic waves pinch on a subsurface conductor like a water bearing veins, they include electric currents in it and they induce basically electric current in it. In the absence of any conductive layer in subsurface conditions, that is suppose we are having quite homogeneous layer and very thick layer, then there will not be any induced current either. So, then in electromagnetic technique is basically based on the measuring of the secondary magnetic field which is produced by the induced current in the conductive layer. So, this is we are introducing the electromagnetic waves, and then we want to like to see that how these waves behaves with different kind of materials present in subsurface condition and how current is induced in these layers. So, there are two types of principles which are employed or methods are there. One is called near field, in which a distance between the transmitter and receiver is much smaller, and the wavelength operating typically in the frequencies between 500 Hz to the 10,000 Hz. And of course, then far field will be there. So, in far field in which the distance between the receiver and transmitter is much larger, longer, and the wavelength even as much as 100 to 200 times a wavelength. So, there are two different near field methods and far field method. The major difference is the distance between transmitter and receiver. And so, in far field method, the fields of distance powerful radio transmitters operating in a very low frequency, that is VLF, from 10 to 15 kilohertz are measured. Because then you have to use the powerful radio transmitters when the the receiver and transmitter are at a very far distance. So, because there will be attenuation of these magnetic waves. So, measurement in this VLF method essentially involve a determination of the tilt of electromagnetic field vector, and this will give us the applications. This is application of electromagnetic method are identifying basically water bearing faults, fissures, crushed zones and veins in bedrock, and if there is a interface between saline and fresh water. So, these methods can be quite appropriate for such kind of conditions, where other methods might not give you a complete insight about the subsurface information. So, even for very thin features say of 1 meter, which can be detected by these methods because of the which provided conductivity at the water it contains is sufficiently high. So, again, like in earlier methods, we have seen through the tables how this will behave. And now we are discussing here the gravity methods. So, after electromagnetic methods, now we go for gravity methods. So, basically what it is doing, it records the variations of acceleration of gravity with a gravity pendulum or a gravimeter, with quite expensive instrument and very sensitive as well. So, and interpret the anomalies in terms of bulk densities of rocks, and depending on the porosity percentage, dry unit weight per cc and specific gravity of solids. So, if we consider igneous rocks, they are having different values here, like weathered or basalt is having completely different than granite. Similarly, for if we consider the metamorphic rocks, then they are having variations in the gravity values, and fluvial deposits like alluvial deposits, sand and quartz are having porosity if they are having 39, then dry and this one is 1.73, and specific gravity of solids might be 2.65. So, different rocks or material will have different, of course, porosity, will have this gram per cc, and of course, the specific gravity of solids will differ place to place or in rock to rock or material to material. So, in gravity methods, as we have discussed just that a gravimeter is used, which is very sensitive, as I have already mentioned this. The gravimeters are very sensitive. Interpretations of or analysis of such results which are acquired requires a number of corrections for effect of elevation, topography, latitude, tides and regional geology. So, all kinds of correction would require before we say that how different behavior and different materials or rocks are behaving in subsurface condition. Topography is very important, latitude, tides and elevations. So, elevations and topography in some way are related here. And of course, in fractured rocks we have also seen in that table, fractured rocks which have lower densities can be differentiated from massive rocks. So, this is the one sort of advantage with gravity methods, that these two variations about the fractures compared to the massive rocks can be easily differentiated because of lower or different densities present in fracture rocks. It will have lower density, in massive rocks it will have high density. So, similarly, the gross configuration of sedimentary basins and the included aquifers can be determined from the basement rocks and differentiated from the basement rock. So, sometimes it is useful. Now, as I mentioned earlier that nowadays a satellite based gravity methods are employed, and to assess the groundwater conditions, what is happening, and the very well known survey was done through this GRACE, which is a gravity recovery and climate experiment, which was a NASA mission which provides the first time that directly measure groundwater changes from the space rather than on the ground, and all kind of corrections which we have just discussed, like the corrections we had discussed, the topography, elevations and other things were performed here. So, what we see here that the in this A, the groundwater storage change rate during pre-monsoon period between that pre-monsoon March-May across India in 2000 between 2003 to 2016. So, this is representing how the groundwater changes have occurred during this period, that is about 13 years time in pre-monsoon period. The second, the B part which you are seeing here, the groundwater storage change rate during post-monsoon period, and post-monsoon period here in this kind of survey or experiment was done taken time is between October-December across India, the same time period between 2003 to 2016, that is those 13 years. Now, the C is important, the overall groundwater storage change rate across India between 2003 to 2016, and that is a very initially when these results came, it was really alarming that in northern India these overall groundwater storage changes are very high, especially in the Indo-Gangetic plain, which you can see that we are getting values of even minus 5 or 6 meters. That means the water table has gone down between these 13 years overall average in this area, especially in northern part. And of course, the D, which is showing the hydrogeological map of India, just to compare how the geology and this GRACE experiments or gravity surface are having a correlation. So, what we see in hard rock terrain, not much changes in groundwater storage between those 13 years when survey was done have been seen, observed, but in case of Indo-Gangetic plain, the maximum changes in groundwater storage have been seen. So, this is really in some way is alarming, and but the recharge is also good in these areas where the lot of changes are occurring. That is why the more changes are being witnessed here also, because first one is showing pre-monsoon, another one is showing post-monsoon. Nonetheless, this is to some extent it is serious that why so much changes are occurring there. Now, by observing changes in Earth's gravity field, it has been possible in this GRACE experiment to estimate changes in the amount of water stored in the region. So, if we talk about Indo-Gangetic plain, which cause changes in gravity. So, if there is a change in storage of water, that will change the gravity. So, GRACE this experiments has provided more than 10 years long, 13 basically 13 years of data recorded for scientific analysis. Of course, no method is perfect by any means, and nothing is universal, no method is universal. So, this survey or this method or this experiment too had some issues, especially about the resolution part and other things, and how errors have been removed about topography, elevations, and whatever the surface features which were present in these areas. So, anyway, this makes a huge difference for scientists and water managers who would like to understand the trends, that how our groundwater resources are being consumed over the long time. 13 years is a quite a good long time to understand this thing. Further, Grace has returned data on the some world's biggest aquifers and how their water storage is changing. And world biggest aquifer is one of them is the our Indo-Gangetic plain also. So, using estimates of these changes based on the gravity recovery and climate experiments in the snow and surface soil moisture, scientists can calculate an exact change in groundwater volume over a region in a given period of time. So, now we are coming to end of this discussion, and so I will quote a study which is a very popular paper which is by Rodell et al. In 2009, which did a more focused study in northwest India, which is a terrestrial water storage change observations from Grace again, and simulated soil water variations from a data by integrating hydrological modeling systems to show that how this groundwater is being depleted, how this water table is going down, and that is again a quite alarming rate. That is, mean rate of this depletion is 4.0 plus minus 1 centimeter per year, which is very significant. And the equivalent height of water, that is 17.7 plus minus 4.5 cubic kilometer per year. So, over the Indian states of Rajasthan, Punjab and Haryana, of course, it also includes Delhi, being a small relatively to these areas. So, here this depletion is quite high because of high population, more requirement of water and more exploitation of groundwater resources, less recharge efforts and so on. So, during this study period, which was between August 2002 to October 2008, the groundwater depletion was equivalent to a net loss of 109 cubic kilometer of water. That much volume of water has depleted in these 6 years, which is double the capacity of India's largest surface water reservoirs. So, whatever the India largest surface water reservoir is there, whatever it holds the water, this depletion is double of that. So, this is in that way very serious, and this also indicates that which are the areas which requires more recharge efforts. So, that the depletion can be checked, depletion can be reduced, and we get the water resources available for longer time. So, with this I end this discussion. Thank you very much.